Have you ever looked up at the night sky? Have you ever felt a sense of wonder at the sheer scale of it all? Billions of stars are scattered across billions of galaxies. Our own planet, Earth, is just a tiny speck in this vast cosmic ocean. Yet on this small blue world, something truly remarkable has happened. Life has emerged, not just simple life, but complex, conscious beings who can look up at the sky and ask questions about their own existence. It's an extraordinary thought. We are part of a universe that has somehow given rise to us, allowing us to contemplate its own mysteries. This simple fact is perhaps the most profound puzzle of all. The question that naturally follows is a deep and compelling one. Why? Why is our universe like this? Why is our universe like? Why does it have the specific set of rules and conditions that allow for planets, stars, and ultimately people to exist? It didn't have to be this way. Imagine a universe with slightly different laws of physics. If gravity were a little stronger, stars would burn out too quickly for life to evolve. If it were a little weaker, stars and planets might never have formed in the first place. It seems we have won a sort of cosmic lottery, a game of chance with stakes so high that they encompass everything we know and are. This isn't just a philosophical daydream. It's a question that touches the very heart of modern physics and cosmology. Scientists have discovered that the fundamental constants of nature, the numbers that govern the strength of forces like gravity and electromagnetism, appear to be exquisitely fine-tuned. Think of the story of Goldilocks and the three bears. She found a bowl of porridge that wasn't too hot or too cold, but just right. She found a chair that wasn't too hard or too soft, but just right. In many ways, our universe is a bit like that perfect bowl of porridge. It's a Goldilocks universe. The conditions are not too extreme in one direction or another. Instead, they are precisely what is needed for complex structures like us to form and thrive. This observation goes far beyond just our planet's position in the solar system, which is also in a Goldilocks zone where liquid water can exist. The fine-tuning applies to the entire cosmos. Let's consider an example. The force that holds atomic nuclei together is called the strong nuclear force. If this force were just a few percent weaker, hydrogen would be the only element in the universe. So how do we begin to unravel this cosmic puzzle of a Goldilocks universe? This is where the Anthropic principle comes into play. In its simplest form, the principle is a statement of the obvious, yet it has incredibly deep implications. Let's break that down with a simple analogy. Imagine you are a very intelligent fish swimming in a pond. This fish might start to wonder, isn't it remarkable that my entire world is made of liquid water? What are the chances that I find myself in an environment that is so perfectly suited for my gills and fins? All life on Earth is based on the element carbon. Its unique atomic structure allows it to form long, complex chains and rings, creating the backbone for molecules like DNA and proteins. Without carbon, life as we know it would be completely impossible. But the existence of carbon in the universe is not a given. It is the result of a remarkable and highly improbable chain of events that takes place deep inside stars. This process is so finely tuned that the great astronomer Sir Fred Hoyle, who first figured it out, was famously shaken by his discovery. He said it looked as if a super-intellect has monkeyed with physics. Carbon is forged in the hearts of aging stars through a process called the triple alpha process. It involves 3 helium nuclei, also known as alpha particles, fusing together. This doesn't happen all at once. First, 2 helium nuclei fuse to form a highly unstable element called beryllium-8. This beryllium nucleus is so unstable that it decays back into 2 helium nuclei in less than a femtosecond. That's a millionth of a billionth of a second. For carbon to be made, a 3rd helium nucleus must strike this fleeting beryllium nucleus at just the right moment. Let's zoom out from the scale of atoms to the scale of the entire cosmos. The universe began with the Big Bang, an event that set everything in motion. One of the most critical properties of the early universe was its expansion rate. This rate had to be exquisitely fine-tuned for a universe like ours to come into being. Think of it like throwing a ball into the air. If the expansion rate 1 second after the Big Bang had been slightly slower, even by a minuscule fraction, the universe would have collapsed back on itself long ago. On the other hand, what if the expansion rate had been slightly faster? If it had been greater by just 1 part in a million billion? the result would have been equally sterile. The fact that our universe sits on this knife edge between collapsing and flying apart is perhaps the most dramatic example of fine-tuning we have ever discovered. Now that we've seen the sheer improbability of our universe, we need to explore how the anthropic principle tries to make sense of it. The principle comes in two main flavors, the weak and the strong. The weak principle is a scientific tool. It helps us correct for a bias in our observations. It tells us not to be surprised by our life-friendly surroundings. The strong principle, on the other hand, is a philosophical statement. It suggests that there is something special about life and consciousness, and that the universe is fundamentally geared towards producing them. So, we are faced with this incredible fine-tuning. The laws and constants of our universe seem perfectly set for life to emerge. How do we explain this? The simplest and perhaps most unsettling explanation is that it's all just a colossal fluke. If the idea of pure chance feels too hollow, there is another explanation that has captivated thinkers for millennia. This is the idea of design. Faced with the starkness of pure chance and the untestable nature of design, a third explanation has really gained significant traction within the scientific community. It's perhaps the most mind-bending of all, the multiverse. This idea suggests that our universe is not the only one. Instead, it's just one bubble, one small part of a vast, maybe even infinite, cosmic foam of other universes. In this grander multiverse, each individual universe could have been born with different laws of physics and different fundamental constants. But with an enormous, possibly infinite number of universes, it becomes statistically inevitable that some of them, just by chance, would happen to have the right combination of laws and constants for life to emerge. Beyond the complex physics and cosmology, the question of why our universe is hospitable to life touches upon one of the most fundamental human drivers, the search for meaning. The answer we lean towards shapes our entire worldview, influencing how we see ourselves, our species, and our future in this vast and ancient cosmos. This renewed sense of our significance comes with a profound responsibility. If conscious, intelligent life is as rare as the fine-tuning suggests, then what has emerged on this planet is of immense cosmic value. Beyond the philosophical and existential implications, the anthropic principle matters because it serves as a practical, if controversial, tool for scientific discovery. A famous example of this kind of reasoning comes from the Nobel laureate physicist Steven Weinberg. He used a weak anthropic argument in 1987 to predict the value of the cosmological constant, and his prediction turned out to be remarkably close to the value that was observationally confirmed over a decade later. This is particularly relevant in fields like string theory, which predicts a landscape of perhaps 10 to the power of 500 possible universes, each with different physical laws. We began this journey with a simple question: why is our universe so perfectly suited for life? The anthropic principle, in its various forms, offers us a framework for thinking about this profound mystery. It doesn't provide a single, easy answer. Instead, it holds up a mirror to our own consciousness, forcing us to confront our place in the cosmic story. It reminds us that any picture of the universe that doesn't account for us, the observers, is fundamentally incomplete. The fine-tuning of the cosmos remains one of the greatest puzzles in science. The strength of gravity, the properties of the carbon atom, the expansion rate of the universe, all seem balanced on a knife edge. Are we simply the beneficiaries of an unimaginably lucky cosmic accident? Did a designer carefully craft a universe with us in mind? Or are we living in just one of countless universes in a vast multiverse where every possible combination of laws is tried out? Each of these explanations takes us to the very edge of what we can know, pushing the boundaries of science and philosophy. We are composed of stardust, forged in the hearts of long-dead stars. And for a brief fleeting moment, that stardust has arranged itself into conscious beings capable of looking back at the cosmos, of feeling wonder, and of asking why. This simple fact is perhaps the most astonishing discovery of all. The search for answers is a testament to the insatiable curiosity that defines our species. The questions raised by the anthropic principle are not just for physicists and philosophers. They are for everyone who has ever looked up at the night sky and felt a sense of connection to the vastness around them. And so, the journey of discovery continues. We are the universe's way of thinking about itself. We are the children of the stars, now grown up enough to begin reading the cosmic recipe book from which we came. The Anthropic principle does not give us the final chapter of that book, but it does give us a breathtaking glimpse of the introduction. It tells us that our existence is intricately woven into the very fabric of space-time, and that simple, powerful idea is enough to fill a lifetime with wonder, inspiring us to keep looking up and to keep asking why.